All right, so we're basically recalling the establishment of the resting membrane potential. And so we'll first start off by looking at the cell here. Let's draw this a little bit higher up. And so what we're referring to here, just bear in mind, is we're talking about a neuron. And just this is what a neuron looks like. So we've got our neuron. It's got more positive charge on the outside at rest and more negative charge on the inside at rest. And so that brings us to negative 70 millivolts. And so we're really talking about how we get to this place. The first thing we want to establish is that on our cell, we've got the sodium-potassium pump. So here's our sodium-potassium pump, really important to establishing this resting membrane potential. Remember, 20% of it is directly owed to the pump, and then 80% of it is going to be indirectly as a result of the pump. We've also got these leak channels. So we've got several potassium leak channels, and then less sodium leak channels. So we've got more of a permeability for potassium than we do for sodium. And just to kind of label our ions out here, so we've got the sodium. Let's draw sodium as these circles. Let's draw potassium as these blue squares, okay? So we know that the sodium-potassium pump pumps 3 sodium out. So we've got our 3 sodium going out and 2 potassium in. And so after the sodium-potassium pump has begun churning, we start to establish relative ion concentrations. So we establish more potassium inside the cell. And then we establish more sodium on the outside of the cell. So let's make a note of the sequence of events here. So the first thing we mention is that we have a higher permeability for potassium, and I'm going to represent permeability with this large P, and then the ion that I'm referring to. So the permeability for potassium is greater than the permeability for sodium. In brackets, I'll put 25 times more, right? We know that there are 25 times more potassium channels on the membrane than there are sodium channels. And so we also know that there's now a chemical driving force because we now have a concentration gradient. So the sodium-potassium pump begins churning, it's pumping sodium out, pumping potassium in. Remember, because 3 sodium are leaving, sodium is positively charged, 2 potassium are entering, we have a net more positive charge leaving the cell than what's coming in. And so that begins to establish the chemical gradient. And so when we look at the chemical driving force, we see that sodium wants to move back into the cell according to that gradient. So the chemical driving force for sodium is going to be into the cell, whereas the chemical driving force for potassium is going to be out of the cell. Okay, so that's kind of the first part of the story, right? Remember, when we look at our overall forces acting on ions, we kind of look at them separately and then we combine them. So the first part of this is the chemical driving force, which is created by the varying concentration gradients that were initially established by this pump on the membrane. So let's just draw our arrows here to show those forces. So we've got potassium wanting to move out of the cell. So that's the CDF for potassium, whereas sodium wants to move into the cell. And this is the CDF for sodium. Okay, let's now consider the electrical forces. So the third step here is that we now look at the EDF for both of these ions. And I want to establish clearly why we end up with a negative environment. So this is kind of the second part of the equation, the indirect 80% with which the sodium potassium pump indirectly contributes to that resting membrane potential. So now we've got a gradient for potassium to diffuse out of the cell passively according to its gradient, and for sodium to move into the cell. But because we have a higher permeability for potassium, more potassium can leave than sodium coming in. And so again, we see a net positive charge leaving the cell. So there's a higher positive charge leaving the cell through the increased potassium channels than there is a positive charge coming into the cell through the decreased sodium channels. So essentially, we've got more positive charge leaving the cell, leaving behind this negative environment. And so we create a negative inside the cell and then a positive environment on the outside of the cell. So I hope we can see how the pump directly contributes to the gradient by pumping more positive charge out, as well as indirectly contributes to the resting membrane potential by facilitating the movement of more positive charge out than what positive charge is coming in. And so now we've got a negative environment inside the cell, a positive environment outside the cell. And so we can now consider the electrical driving force, which we know depends on the charge, on the ion, the charge of the cell. And so the electrical driving force for sodium is going to be into the cell, right? Sodium is positively charged. It wants to get into the negative environment inside the cell. So let's reflect that here with a second arrow. So this is our EDF for sodium. And then if we consider potassium's electrical driving force, it will also be into the cell because potassium is also positively charged, wanting to get into that negative environment inside the cell. So again, potassium's EDF will also be into the cell. And so we'll reflect that with a second arrow here. And so this is the EDF for potassium. And so now the fourth step is combining those two forces, right? We talked a lot about that algorithm, what we do when we've got two forces acting on a particle. If they're in the same direction, we simply combine those two forces. So sodium, it's going to be pretty easy. We combine the two forces. We simply add those two values, and then the overall direction will be in that general direction. So we can say that the ECDF for sodium is going to be a stronger force into the cell. Whereas the ECDF for potassium is going to be a weaker force out of the cell. And I'll explain why it's going to be a weaker force here in a minute. So this is going to be a weaker force out of the cell. Okay. And the reason it's going to be a weaker force is if we look at the separate forces acting on potassium, we've got a CDF out of the cell, an EDF into the cell. And if you remember back to that algorithm, if our forces are in opposite directions, we're going to subtract the smaller force from the bigger force. And then we're going to take the overall direction to be in the direction of the greater force. And so again, thinking back to the rules of that algorithm, in order to figure out which is the bigger force, we have to now look at the membrane potential and compare it to the equilibrium potential. So the equilibrium potential for potassium is -94. Whereas the membrane potential is -70. And so comparing these two values, the equilibrium potential is the bigger value, right? Remember, we're looking at the equilibrium potential specifically for potassium. And so because this is the bigger value, the overall force will be in the direction of the chemical driving force, which will be out of the cell. Okay, and then we simply subtract that 70 from 94, and that's going to be the magnitude or the strength of the force, which as we can see is going to be weaker than the overall combined force for sodium. So sodium really wants to get into the cell. There's a stronger force pushing sodium into the cell, whereas potassium has this opposing force trying to drag it back into the cell. And so it's going to be a weaker force overall out of the cell. Okay. And so that's our ECDF, so the net movement of our ions. And so after these ions begin moving in this general direction, we then establish what we call steady state, which is where there's no longer a net accumulation of ions on either side, and things just balance out. So we've gotten to steady state. And at that time, if we measure the membrane potential, that is how we arrive at our -70 millivolts. Okay. There's one point that I really want to drive home as far as the equilibrium potential. So I got a question that was really interesting, and it asked whether or not both ions could be at equilibrium. And the answer is no. Remember, the equilibrium potential of an ion is when the membrane potential reaches that value, and so there's no movement of our ions because the forces themselves are in opposite directions and they cancel out. So both of the ions are trying to get to their equilibrium potential, but because we have to take both ions into account, neither of them will actually get to that equilibrium potential. Instead, the cell is going to settle on a value that is shared between both of those equilibrium potentials. And so -70 is kind of the middle ground between sodium's equilibrium potential and potassium's equilibrium potential, but it's closer to potassium's equilibrium potential. And the reason is because we have more potassium channels. So potassium can move more freely across the membrane. And so when the cell is at rest, the membrane potential is going to look a little bit more like potassium than it will look like sodium's equilibrium potential. Okay. The second point that I want to drive home here is that because sodium's overall ECDF is really strong and into the cell, we have the membrane potential is further away from sodium's equilibrium potential. And so the force to move sodium is going to be stronger because at rest, the cell is really far away from potassium's equilibrium potential. Whereas for, that was for sodium. Whereas for potassium, because the equilibrium potential for potassium is negative, it's also closer to the resting membrane potential. The movement of potassium is going to be less aggressive because it's further away, because it's closer to its equilibrium potential than sodium, for example. Okay. And we'll go ahead and clarify that a little bit more on some of the upcoming slides, but I really want to point that out here as we look at the overall ECDF for potassium.